Okay, so before we start, last time we agreed with a couple of people that they will make talks, give talks, and so there are at the moment there are three potential topics, and the first one is Quillen equivalence. The second one is transfer of model structures, and the third one is Bousfield localization. Now, I think the third topic will be covered by R-shock, and let's decide about the first two. Sorry, I forgot your name. Misha. So Misha already knows something about model structures. Probably, I think Misha will be able to cover the first one, but I would like Misha to learn something more. So I would like to give the second topic to Misha, which means somebody else would have to cover the first topic. Are there any volunteers? Okay, so very well. What's your name? Alexei. What's your last name? Okay, so the preliminary plan is for Alexei to talk about model structures, just basically only covering the ingredients we need to prove Quillen's theorem, which says that a Quillen junction is equivalent equivalence if and only if, and then there are several ways to state the conditions. And there are, by the way, several ways to state what it means to be what it means for a couple of functors between model categories which are adjoined to be equivalent junction. For example, the one condition is the left adjoint preserves cofibrations and acyclic cofibrations, and the other condition is the right adjoint preserves fibrations and acyclic fibrations. Well, those are equivalent. Transferred model structure is well, it's a bit more difficult, but there are references, and Misha, I would like you to. We'll talk about the references. So the idea is to prove that the right transfer of model structures works if some conditions are satisfied. And actually today we'll mention one of those, and the remaining ones are more or less general nonsense, and we'll mention the one that really needs to be checked. So the plan is let's have a look at the references, and if those really don't make any sense at all, then we'll think of something else. And this something else could be, at least stating the result and explaining all ingredients. Okay, so far the topics are all three are related to model structures. But this is not all we want to cover. Is there anyone who knows? Is there anyone here who knows complex geometry, or who would like to know something about complex geometry? There's another topic which is I think well, you're not interested. Okay, so we have another we have enough material about localization planned for the rest of the term. So. The fourth topic would be to explain the at least the plan of the proof of the following theorem. It turns out that compact Kähler manifolds are formal. Formal in which sense? It turns out that the minimal model for the forms is the same as the minimal model for the cohomology, which we can view as a differential graded algebra with zero differential. Okay, now the result. This result is proved in this paper over C, but there are several generalizations. For example, one can replace C by Q. The cohomology, the rational cohomology of a compact Kähler manifold is quasi-isomorphic to the PL differential forms on any smooth triangulation of the same manifold. It's another interesting result, and if there are people who would like to talk about that, then it's a topic for a separate talk. Now, one can replace Kähler by meromorphically Kähler. So well, for example, there are complex algebraic varieties which aren't Kähler, which is a pity, or maybe not. But anyway, this theorem doesn't cover all complex algebraic varieties. On the other hand, by Chau's lemma, every complex algebraic variety can be blown up to a projective one, hence to a Kähler one. So, are there any people who would like to talk about this? No. I'm sorry, what's your name? Andrei. Do you know anything about Kähler varieties? Do you want to know more about Kähler varieties? Ну, значит, давайте с другой стороны начнем. Значит, встречалось ли вам определение Kähleровости? Ну, это уже хорошо. Значит, встречались ли вам операторы, значит, дельта и дельта с чертой? Значит, а вот есть такая еще дельта-дельта с чертой лемма, которая, ну, значит, по сути, эквивалентна Kähleровости. Вот, значит, тогда у вас все козыри на руках. Значит, что это означает? Это означает, что, значит, ну, фактически, глядя на эту лемму, применяя линейную алгебру, мы можем вывести вот это утверждение, значит, вот это утверждение на C. Давайте сейчас забудем про обобщение, там, бимероморфное и так далее. Значит, на C мы вот кроме dd с чертой леммы ничем не пользуемся. Дальше. Значит, то, что не доказывает, если dd с чертой леммы выполнено, да, значит, если у нас есть бимероморфное отображение, то есть отображение степени 1, все гладко компактно. Значит, если dd с чертой леммы выполнена внизу, она выполнена наверху. и наоборот. Значит, если выполнен наверху, выполнен внизу. Значит, это какая-то линейная алгебра, опять же. Вот, глядя на это все, пользуясь этим, мы получаем вот ровно то же самое утверждение, пока на C для произвольных бимероморфных Келлеровых многообразий, значит, ну, в частности, для произвольных комплексных компактных многообразий. В общем, Андрей, я предлагаю вам значит, взять эту тему, поскольку какие-то слова и даже, наверное, большая часть нужного материала вы уже где-то видели. Ну, доклад нужно делать на английском. Значит, никакой проблемы. Значит, ну, нужно учиться. Нужно в общем, как любое другое занятие, оно, ну, значит, оно там требует упражнений, и после этого я не говорю, что будет получаться вот точно так же, как по-русски, но что-то будет получаться, и это такой навык, который в жизни, ну, математической жизни, он ну, фактически необходим, то есть там без этого сложно общаться. Okay, so the fourth topic would be the fourth one is taken by Andre. Okay, so we have 4 topics and 4 speakers, which is a success. But then there are versions, variants, generalizations, and so on. So if there are people who want to give a talk, including those listening to the broadcast, please let me know. So there are several related results which it would be interesting to talk about. Okay. Any questions? Or suggestions for other topics which I didn't mention.
We can ask you for references.
Yes, absolutely. Well, this one, the first one, I think the easiest way would be to take the paper by Dwyer and Spalinsky. Misha, what's the name of this paper? Yes, so that's the one. In this paper, there's a section about Quillen equivalence, and in the section there's a theorem. So we want to know basically all the ingredients which are needed to state the theorem and to prove the theorem. Okay. Are there any more questions? Anyhow, if you want to give a talk about something related or something unrelated to this, but still related to localization and rational homotopy, please let me know. Okay, now let's let me say a few words about something I mentioned at the end of last week's class, but didn't cover properly. Co-chain complexes. There are several versions. I will just describe them, and the ones that occur in practice most of the time are bounded complexes. Now there are two types of bounded complexes: bounded below and bounded above. Now let's think about complexes which are bounded above as chain complexes. So we have we have complexes which are bounded, which are concentrated in non-negative degree, but the differential lowers the degree. And this in this case, we have the projective model structure. The weak equivalences are always quasi-isomorphisms. For the projective model structure, the fibrations are degree-wise surjective maps, and the co-fibrations are degree-wise injective maps with projective co-kernel, meaning in each degree the map should be injective, and the co-kernel should be projective. For co-chain complexes, there's a similar story. There's the injective model structure in which the weak equivalences are the same. The co-fibrations are degree-wise injective maps, and the fibrations are degree-wise hypermorphisms, and the kernel of each of those should be injective. There are versions of both for but we need to replace injective by k-injective in this definition, where k-injective means hom into it takes acyclic complexes to acyclic complexes, and every co-chain complex which are degree-wise injective and which is bounded below is k-injective. But if we do not assume that the complex is bounded below, this is no longer necessarily true. And similarly, k-projective means hom from it takes acyclic complexes to acyclic complexes. Where by hom I mean the hom complex. And again, if we have a chain complex of which is bounded below and which is degree-wise projective, is k-projective, but if it's not assumed bounded below, then who knows? Okay, I don't want to. I don't want to talk about the unbounded case too much. We don't really need it. And also note that the if we're over a field, in particular Q, then all modules are both injective and projective, which simplifies things. So, in particular, if we take this model structure on co-chain complexes and transfer it to CDJs, we get a model structure on CDJs. Well, let's we have already seen how to construct a model structure on topological spaces, on chain complexes. Let's see how it works for CDJs. We need to use the there are several ways. Before I talk about the right transfer, I should mention I should mention that it's perfectly possible to construct this model structure by hand. This is what Gelfand and Manin do in their book about methods of homological algebra. The book is called blah, blah, Methods of Homological Algebra Volume 1, and there is no Volume 2, just Volume 1. I think the last chapter is called homotopical algebra, and in this chapter they talk about model structures, and in particular they construct a model structure on CDJs from the first principles. However, it's often quite difficult to construct a model structure by hand. There's lots to check. People have discovered a few industrial recipes or some people would say, scalable recipes to construct model structures. Let me talk about one of those. Suppose we have no. I want this one to be the left adjoint. Suppose we have two adjoint functors. And the left adjoint is L and the right adjoint is R. Very well. So suppose we have a model structure on C. And we want to define a model structure on D. Let me write let me write a candidate here. So I have a model structure on C. I want one on D. I take as weak equivalences all morphisms which go to weak equivalences under R. And similarly, the fibrations I declare the fibrations in D to be precisely those maps which go to fibrations under R. Now comes a question. We know that the fibrations and the weak equivalences determine the cofibrations in a model structure. But this doesn't mean that I can take more or less anything as weak equivalences and something else as fibrations and declare the result to be a model structure. This doesn't always work. And which is not surprising, but the good news is it often does work.
Sorry, but how this definition with adjoint structure on functors?
It doesn't. But for the moment, we just use the fact that we have one functor going from D to C. But of course, when checking that the right transfer works, we need the functors to be adjoint and more. And Alexei will explain no, Misha will explain when we'll give sensible sufficient condition for the right transfer to work. Okay, so let me first state the example we want to apply this to. And by the way, there's a word "right" there that didn't attract attention. Well, there is a symmetric notion of left transfer, meaning suppose we have the same diagram, but we have a model structure on D, and we want to construct one on C. Then we just interchange D and C in this definition, but we also replace R with L, because otherwise the definition wouldn't make sense. And we replace the fibrations with the cofibrations. The left transfer is not as useful as the right transfer. And at least in algebraic in the algebraic context. And this has something to do with the fundamental asymmetry in mathematics, about which I don't want to talk, not now anyway. So we'll focus on the right transfer, well, because in practice it's the one that people use more often than the other one. Okay, so here is the example we want to apply all this to. So we have a model structure where we have a model structure on C, and we need one on D. So C let's take all non-negatively graded co-chain complexes on C as C with this model structure. And let's take the category of all CDJs. Again, we assume that those are non-negatively graded. Well,
corresponds taking zero covariance. Yeah.
well, let's look at the functors. So we need a right adjoint and a left adjoint. So the right adjoint goes from CDJ to chain complexes or co-chain complexes, and this is just the forgetful functor, and there's nothing very mysterious about it. Now we need a free functor. A left adjoint. The left adjoint is the free functor. Given a non-negatively graded chain complex, co-chain complex, we construct we construct a CDGA using the trick we already saw a couple of times. I can always, if I have a graded vector space, I can always take the free algebra over Q generated by this vector space. It depends on the definition of symmetric. Starting from a graded vector space, we construct the free algebra generated by this vector space. Now, the free commutative graded algebra generated by the graded vector space. So it's as an algebra, it's is the symmetric algebra on the even components, tensor the exterior algebra on the odd components. No surprises there. Now I want to be able to turn this into a graded into CDGA. So I need a differential. If I have a differential on V, I can construct a differential on lambda V using the Leibniz rule. And the resulting thing would be a commutative differential graded algebra. This is not completely for free, but it's not too difficult to check, and this resembles one of the this implication resembles one of the questions in the problem sheet. Okay, so we have the free functor. Now those two functors are adjoint. Again, it's a relatively straightforward check. Now we have a model structure on chain complexes, so we get a candidate model structure on CDJs. Let me write it down. I will not write down the full description of the model structure, but I will describe most of it. So we have a candidate model structure on CDJ. The vibrations are just sorry, the weak equivalences are just quasi-isomorphisms. The vibrations are component-wise surjections. We don't need to worry about the kernel being injective because over a field all modules are injective. And the cofibrations are cell attachments. Actually, no, this is not what I said. The cofibrations include cell attachments. So let me explain what one cell attachment does. Suppose this is basically what we have in the first problem sheet. So suppose I have a CDJ. And suppose I have a graded vector space which is concentrated in just 1 degree. And suppose I have a map from V to A, which ends up in cycles. In the cycles of A. What do we do with this map? Well, let me call this this map dV. Then I can do the following thing. I take the algebra A, tensor it by the exterior algebra generated by V. I define the differential on A, on V, and the question something from the problem sheet tells me that this is the result is in fact a CDJ. Okay, so what do we have? We have at least a partial description of cofibrations. We don't know what all cofibrations are, but we have some examples. Now, to get more examples, we can compose several elementary cell attachments. We get another cofibration, and there is also a way to compose infinitely many cell attachments. and I will not I will not talk about that, but probably one of the speakers will. Basically, in this example, we have a particularly nice model structure, which is a cofibrantly generated model structure, and this is part of the general theorem. If the model structure on C is cofibrantly generated, then so is the transfer model structure. And then once we have defined transfinite or transfinite, I don't know, compositions of cell attachments, we need to take the retracts, and we basically get all cofibrations. Okay, are there any questions? Let me mention the main ingredient, why this works. What I will mention today will simply look as a fun statement, which may be useful, but maybe not. And later on we'll later on we'll see where exactly this statement comes in. As we will see, the main thing which is needed to check, which we need in order for this to work, is the surjective trick. Let me state the surjective trick. Suppose I have a map of CDJs. Then my claim is that this map decomposes as first a quasi-isomorphism from A to A tensor E. We'll come to that. And secondly, a surjection from A tensor E to B. Now, Yes, so basically it's a very particular case of it resembles, no, it's not even a particular case. It resembles the it resembles one of the factorizations. Every map is can be decomposed as an acyclic cofibration followed by a fibration. And well, we don't know yet anyway, no, actually, it is a particular case of the factorization property. But let me. Let me first explain what E is. We have E equal lambda of B dB. Now, what does this mean? Well, basically it means what it says. B B in this formula is the algebra B, which is viewed as just a graded vector space. Actually, okay, so if I have a graded vector space, I can shift it upwards by 1 and get another graded vector space. And then I declare the differential on the generators to be the identity map from B to dB given by D. And the result would be the product of a product of maybe infinitely many copies of the following algebra. I take some generator. I take D of this generator, and I span the free graded commutative algebra using these two. Now, the very important thing which happens here, and which doesn't happen over other rings, is that this okay, so let me somewhat belatedly change the brackets. Now, whatever the degree of x, the cohomology of the resulting algebra is the same as basically Q. And after some work, we conclude that this algebra is also has the cohomology equal Q. Well, let's see. So we have defined E.
Sorry, but where did you get X's?
The X's are a Q basis of B as a vector space.
As a vector space,
Yes. And there exists a surjective CGGA map from this algebra to B. Every element of B viewed as a vector space just goes to itself as an element of B as an algebra. No surprises there. Well, what about this one? Well, every element of B as viewed as an algebra has a differential. And we define the map on dB so that we get a map which commutes with the differentials. Would you like me to explain this in more detail? Okay, so we want to define f on dB, where this dB should be formally viewed as a single single notation. Okay, so So every element of dB can be formally written as d times element of b. Then we take this this element to d of b, but this time we apply the differential in b. Does this make sense? Okay, now we can decipher all the maps in this diagram. First, I identify A with A tensor Q. Then I do the identity of A times the inclusion of Q into E. Then there are two F's. Let me call this one G. Sorry. Okay, then I take F tensor G. No. Yeah, something is not quite right here. Well, so if I apply F tensor G, I get a map from A tensor E to B tensor B. Okay, but then I take the product. And I end up in B. Okay, so this gives me a decomposition as I want the decomposition I'm after. I cannot yet claim that this thing will be a cofibration because I haven't yet proved that the cofibrations are what I said they are. But it doesn't really matter. Once we have this, we need to check a few more things which are which have to do with general nonsense, and we get the model structure. So the surjective trick is actually quite useful on its own, even if we don't worry about whether or not there is a model structure. Okay, so I suggest we have a break now, and then we'll continue talking about the benefits of having a model structure on CDJs. Так, значит,
Да, то есть любое построение модельной структуры достигается в итоге ноль. Что это какое-то вложение А в А транзакции. Ну, в смысле, вложение в
значит, значит, если, значит, вот такая факторизация это очень частный случай модельной, значит, того, что требуется в модельной структуре. Но оказывается, что этого достаточно. Значит, ну, по модулю каких-то значит, утверждений из области значит, general nonsense. Okay, so we have seen we have just seen the surjective trick. I would like to point something out. This statement is true over Q, and not true over Z localized at a prime number, which makes which is what makes the homotopy theory over Q much easier than the homotopy theory localized at a prime or basically localized anywhere but everywhere. Anyhow.
So we only use field structure in this statement.
I use the fact, more precisely to prove this, I use the fact that all positive integers are invertible.
All positive integers are invertible. Okay.
Basically, if we look at this algebra, then we just
all positive integers. This fact not work on
well, here not all integers are invertible. B is not invertible here.
No, I asked about what this fact is characterized by probability or not.
Say again? I did not understand the question.
We use field structure.
We use finite fields. Well, an exercise. This is not true over any finite field. And the reason is the characteristic is not invertible. Well, let's take x of degree 0. Then we basically get polynomial forms on the integral on the interval 0, 1. And it's a fun exercise to prove that the algebra is contractible, and when one way to prove this would use integrating the powers of x from 0 to 1. So So this integral is equal to what? From 0 to 1, x to the nth dx. Say again? 1 divided by. Yes, so we see that the result involves dividing by something, and this is basically why the homotopy theory is so complicated. If this integral were 1, the homotopy theory would be much simpler. Anyhow, so let's go on. In model categories, there's a general notion of a left homotopy and a right homotopy, and as a particular case of this general notion, we get the following. Such that so two CDJ maps are homotopic by definition. If and only if there is a map from A to B tensor the forms on 0, 1. So I take just the algebra of forms on 0, 1, on the interval 0, 1 with rational polynomial coefficients. And this is what I mean by lambda x dx, where x is in degree 0, such that f composed with the evaluation at 0 is small f, and f composed with evaluation at 1 is g. Well, the evaluation at 0 and evaluation at 1 are precisely what you think they are. They're CDJ maps from B tensor lambda x dx to B, and the element of this lambda is some is either a polynomial or a polynomial times dx. Well, polynomials times dx go to 0, and the polynomials without the dx go to the value at 0, respectively 1. Does this make sense? Имеет ли смысл то, что написано, или это нужно еще более подробно разъяснить? Значение. Значит, у многочленов есть значение в нуле, в единице. Now, as we will see in the general story, this algebra B times the forms on the interval is a path object for B. Okay. Now, a natural question once we have this definition is whether this is an equivalence relation. And the answer is no. But it is if A is Sullivan. Now, what does the word Sullivan mean? Well, this means it's obtained by It's a CDJ which is obtained from Q by attaching cells. We know that cell attachments are cofibrations. We don't know how to describe all cofibrations. What we know are some examples of cofibrations. So now I want to explain why we have an equivalence relation if the source algebra A is Sullivan. To begin with, I want to define all words I've just written. In a model category, normally we have some objects which are better than other objects, and objects which are both fibrant or fibrant and cofibrant, respectively cofibrant, are particularly good. Let's define those. So we say here that Sullivan algebras are cofibrant. What does this mean? Well, in a model category, there is an initial object and a final object. We require that all limits, or at least all finite limits and co-limits, should exist. Well, the initial object is the co-limit of the empty diagram. The final object is the limit of the same empty diagram. In sets, the initial object is the empty set. The final object is basically any one-point set. They're all they're all isomorphic. but there are lots of them, and the empty set is really unique. Why? Well, suppose there were two empty sets, then each of those would contain all elements the other one does, so they're the same. Okay, so in a model category C, so A in C is cofibrillant if the empty set to A is a cofibration. And symmetrically, an object is fibrant if the unique map to the terminal object is a fibration. So we can now specialize all this to C equal CDJ. What's the initial object? What's the initial object for the category of Q CDJs? Just Q, yes. What's the final object? So there are two proposals. One is Q and the other one is 0. So which one is correct? 0, yes. So the final object is 0, which is also a Q algebra and a ring and a unital ring in which 1 happens to coincide with 0. No, definitely not. Well, in an abelian, it's not additive. It's not additive. Maps of objects of an additive category form an abelian group. An additive category is a category enhanced in abelian groups. Very well. Well, maps of CDJs are not an abelian group in any meaningful sense. Okay, so we do have a final object and an initial object. What do we do? What do we do with those? Well, okay. Now, let me first let's state. I want to. I will state what I need in order to prove this, and then we will see how it follows from the axioms of model categories. So suppose I have I have a Sullivan CDJ and a surjective CDJ map. Let's assume that this map is not just a map. Let's assume it's a quasi-isomorphism. Then my claim that any map, any CDGI map F from A to C can be lifted to B. In other words, there is an F prime from A to B, such that the diagram commutes. Okay, so how does this follow from the axioms? We want to see whether the axioms are any use. Maybe they're just useless axioms, which and maybe we're just wasting our time. Well, let's see. I have these two arrows. Okay, I'll draw the diagram again. No, this one is supposed to be a C, B, and here I will put the initial object. The initial object always maps to any other object in a unique way. The diagram commutes for obvious reasons. There is just one map from the initial object to any other object. Let's remember the axioms. We're looking for for a map f prime and the axioms tell us that sometimes we do in fact have an f prime such that if we insert it in the diagram, both triangles will commute. So, what when is this possible? What do the axioms say? Well, let's remember what the axiom says. Значит, что нам говорят аксиомы модельной категории? Значит, мы хотим их применить, но мы сейчас не помним, что они говорят, поэтому мы ничего применить не можем. Yes, so the axioms of model category say that there exists a lift if the arrow on the left, the vertical one on the left is a cofibration, and the vertical arrow on the right is a fibration, which is also a weak equivalence. Okay. Now, let's think if we need to okay. In fact, once we know that Sullivan algebras are cofibrant, we also know that the homotopy relation is an equivalence relation. So we don't really. Let me write this down. Okay. So once we know that Sullivan algebras are cofibrant, we basically do not need we don't need anything anything else. But there is a direct way to prove this. Do we want to do this? Probably. There is a direct way to prove this, but let's skip it. To prove this, that a homotopy is an equivalence relation on CDJ maps from A to B. Where A is Sullivan and B is arbitrary. What else? Let's think. So actually, this statement here is useful on its own, but we will not use it to prove this. Why not? We've decided to skip it. Well, I've decided to skip it. Actually, if there are people who would rather not skip it, please let me know. Well, for example, some people are asleep and they don't really mind either way. Anyhow. The one of the main points of having a model structure in the first place is constructing the localized category. So suppose we have a model category C. And we want to, probably time to close the window, and we want to localize in W. We want to take C and localize in W. And the localized category is constructed as follows. Remember that in the general construction of the localized category, there was there was the tricky question how to construct morphisms, and well, it's pretty straightforward to do this, but then we have essentially no control over what we end up with. Where? Where CA is A cofibrant replacement of A, and FB is A fibrant replacement of B, which means we have which means basically that FB is fibrant, and we have a weak equivalence between B and FB. And as I said, there were two notions of homotopy. Oh, sorry. We just take a cofibrant replacement of A fibrant replacement of B, and we take all maps from one to the other, and we quotient out by the equivalence relation of left homotopy or right homotopy. It doesn't matter which one. And the same. So this is a theorem which we will probably learn from Alexei Stok. Let's specialize this to our case. Well, every map from an arbitrary CDJ to 0 is surjective. There is no doubt about this. Well, so how to compute CDJ with quasi-isomorphisms inverted from A to B. Well, it's the same as CDJ A prime B where A prime is a Sullivan model for A. And we have already seen that such models exist basically in for a reasonably large class of CDJs, basically for all CDJs, such that H naught is Q. In particular, if A has a Sullivan model, then we don't need to look any further. We take Homs from this model to B. We don't need to change B. It's automatically fibrant or fibrant, and we identify. We take all maps and we identify those which are homotopic. Okay, so assuming we have a model structure, we have a more or less explicit description of the homotopic category. Okay, so let's remind ourselves of our goal. We want to prove that this homotopic category of CDJs is equivalent to the category of topological spaces localized at those maps which induce isomorphisms of the rational homotopy groups or the rational homology. Well, in both cases, we need to restrict our attention to an appropriate subcategory. For CDJs, we need to take CDJs which are connected and simply connected, and for spaces, we need restrictions of the same type. And fundamental group complicates everything. No surprises there. Okay, so this is our goal, and we have constructed we sort of constructed a model structure on CDGAs, and now we need to compare it with spaces. And there's unfortunately the only way I'm aware of passes through simplicial sets. So does everyone know what a simplicial set is? Okay, so there are two functors. Okay, a preview of what probably will happen next time. So, Alexei, if you are ready, if you're ready by next time, by next week, then it would be a good idea to have your talk next week, because I've said a lot about model categories, but I haven't proved anything. On the other hand, if you're not ready, I'll just continue continue where I left where we left off today. So basically, we have topological spaces, simplicial sets, and CDGAs. Okay, so let me like this. So we have a left adjoint functor so we have an adjunction, in fact, equivalent junction between topological spaces and simplicial sets. So the left adjoint is the fat the thin geometric realization, and the right adjoint is the singular simplicial set. Here, the left adjoint is something which generalizes a little bit rational polynomial forms, and the right adjoint is the geometric realization functor, which we'll talk about. The first adjunction is equivalent equivalence, and the second one is not quite equivalent equivalence. We need to restrict to an appropriate subcategories here and here. Okay, so are there any people who need to go to IUM? Сегодня нет лекции, а почему?
Просто Вася куда-то, в общем, ретировался.
Вася ретировался, а Федя?
Сейчас часть курса читает Вася. Или сегодня проводит консультацию по решению задач. Типа семинара.
Консультацию, ну хорошо. Так, ну тогда я предлагаю еще сейчас, значит, так, хорошо, значит, давайте обсудим, значит, вот эту часть, она простая, следующий раз. Значит, все ли понимают, что такое симплициальное множество? Значит, на уровне определения. Там, значит, пока не ошибали глубоко, мы не претендуем. Okay, so we basically my suggestion was let's have a look at the first adjunction and then talk about the other one next time. So we let's look at the. So we have simplicial sets. Now, singular simplices of a topological space form a simplicial set. Does this sound surprising? Okay, so we in the opposite direction for every simplicial set we can form its thin geometric realization, which basically consists in taking in viewing all components as sets of simplices, and then identifying the faces which according to the face indigenuous maps. Now, the well, the space obtained by taking the simplices and then the geometric realization is very, very big. But it maps into X. And this map is always a weak equivalence. A weak equivalence in the usual sense for topological spaces. And actually it's a non-trivial theorem. Well, it's not particularly complicated, but still non-trivial. But it's useful. Anyway, so the this thing is a weak equivalence for every x. And then to be able to say that the other one is a weak equivalence, I need to talk about weak equivalences of simplicial sets. But a map of two simplicial sets is a weak equivalence if and only if the map of the geometric realizations is a weak equivalence. For every k, I don't need in simplicial sets. Not all objects are fibrant, but all objects are cofibrant, and I need to apply the left adjoint functor, so this works. And in topological spaces, the map into a point is a self-vibration. So all objects are fibrant. So I'm allowed to take arbitrary elements here. I don't need arbitrary spaces here. Don't need to modify anything. Okay, so it's a non-trivial but not very difficult theorem that this thing is equivalent equivalence. Tongue twister. We'll talk about the other adjunction next time, and unless Alexei is ready, and then we'll try to see why the second adjunction gives us an equivalence of some subcategory of the homotypic category here, and similarly on the right. Okay, are there any questions? Well, let's call it a day.